So now we're gonna go over optimization problems in general. Optimization, mainly this is when you are trying to maximize or minimize a certain function. So your goal may be to maximize the output, maximize profit, maximize return, or to minimize another objective function like minimize the cost of production, minimize waste, minimize risk, like the standard deviation of a portfolio, and so on. Now, in each of those optimization problems, you have three major things to determine. First of all, you have your decision variables. So let's say you have x1, x2, x3, and so on. So those can be, let's say, the number of output of different types of products, or they can be the weights allocated to different assets or different securities in your portfolio. So mainly we're gonna use solver in Excel to generate a solution for those decision variables. The second thing I need to have is the objective function. So the objective function can be to maximize, let's say, profit or return, or to minimize cost or risk. And in any case, those functions are gonna be expressed in terms of the decision variables. So my decision variable, x1, let's say the number of products of unit 1, x2, the number of product 2, and let's say I can make a certain profit or I can sell those units for a certain price, then the objective function for the revenue or for the profit is going to be a function of the price I'm getting or the profit I'm getting in addition to those decision variables x1 and x2. Finally, I'm going to have what I'm going to call as constraints. With any optimization problem, we're going to have a set of constraints because otherwise, in many cases, the answer may be infinity, especially with maximizing a certain function. Because mainly, if I don't have any constraints, you're going to see that you should, like, your level of output should be infinity. If you are assuming that you are able to sell all of the products you are producing and that raw materials and whatever input is available for you with no issues, uh, and that you don't have a time constraint because for many production, let's say, problems, at least you're going to have the time constraint. So if you have, let's say, a factory, the factory is operating 24/7. Now, if given the number of machines you have and how much time you need to produce each product, there's a capacity limit on how much you can produce per week, even if you are operating all the machines at full capacity 24/7. So at least we're gonna have a certain number of constraints. So now let's start with our first example. In this example, we have a manufacturing company that produces two products, one and two, using three raw materials, A, B, and C. The objective of this manufacturing company is to maximize the weekly profit subject to the raw materials constraints. So here I have in the first table the profit per unit of products one and two and the production requirements per unit, like how many units of each raw material I would need to produce product one or product two. And here I have like what the 1,800, 750. Those are the available weekly quantities of each product. Now, of course, you may say that if you need more, you can buy more from those products. But let's say that you already have some long-term contracts in place with suppliers and that you are able to get, let's say, 1,000 units of A or 1,000 pounds of A for a very competitive price. If you want to demand more, buy more from the market, you're gonna end up paying significantly a higher price, and therefore it may not be profitable for you to add to that original 1,000 pounds or 1,000 units of A. So now, given that for each unit of product one, you are able to make a profit of $12 a unit, for product two, you are making $8 a unit, your objective is to maximize your overall profit, your overall weekly profit from selling all the produced units from product one and product two. So here, mainly, if I didn't have those limitations or those constraints regarding the availability of raw materials or input, my answer is going to be infinity. Like I should produce an unlimited number of product one and product two. And this, in this case, my weekly profit would be also unlimited. So here, let's start step by step. The first step, my decision variables are first X1. I can define X1 as the number of units of product one produced weekly. X2 is going to be the same, but it's going to be for mainly product two. So those are the decision variables. And as you can see here, I have, like in that second table, I have decision variables X1 and X2. And initially, I'm leaving those cells here blank because I'm gonna be using solver in order to generate a solution into those two cells. The second thing is gonna be the objective function. So in this case, clearly my objective function is to maximize weekly profit. But I need to write weekly profit as a function of X1 and X2. Now here, in order to write this as a function of X1 and X2, I need to look into the profit per unit from each product. So now whenever I'm selling 1 unit of product one, I'm making $12 a unit. So if I'm going to produce X1 units of product one, my profit from product one is going to be 12 times X1. So here I have 12X1 is mainly my profit from selling X1 units of product one. Then I add the profit resulting from selling X2 units from product two. So here I'm making $8 on each unit of product two. So if I'm producing and selling X2 units, I still don't know like what are the values of X1 and X2, but once I get the solution, once solver generates a solution for X1 and X2, I can know what would be my actual maximum weekly profit. So for now, I'm gonna write this as 12X1 plus 8X2. So this is for the objective function. Then I'm gonna write the constraints. What are my constraints? So regarding the constraints, I have the raw material constraints. The first constraint is regarding the availability of raw material A. Now, for this constraint, I'm gonna use a certain quantity or a certain number of units of raw material A. However, the amount that I'm gonna use should not exceed 1,000 units, or let's say 1,000 pounds. So in this case, I need to put that the actual quantity used of raw material A should be less than or equal to 1,000. Now, how many units of A I'm gonna need? It's gonna follow the same reasoning that I had with the objective function. So mainly for each unit of product one, I need 2 units of A. So if I'm producing X1 units of product one, I'm gonna need 2 times X1. The same for product two. For each unit of product two, I need 3 units of A. So I would simply multiply 3 times X2, which is gonna be the actual number of product to produce on a weekly basis. So here I can write the following: 2x1 plus 3x2. This should be less than or equal, I'll write it this way, to 1,000, which is the available number of units. Now, for the second raw material, it's gonna be the same. So it's gonna be 5x1 plus 2x2 less than or equal to 800 units. Now for raw material C, I have 1 times x1 or x1 plus 4x2 should be less than or equal to 750. So those are all the raw materials constraints. However, in this problem, I still need to add a final constraint, which is the non-negativity constraint. Because like the minimum number of units of product one that I should produce is 0. I cannot produce any negative quantity. So in this case, I need to add this non-negativity constraint and state that x1 and x2, they should be greater than or equal to 0. Now, in certain problems, I may need to add some additional constraints. Like, for example, if you are working with a human resources problem, you are allocating employees and managers to different branches. So let's say that you are operating a like large retailer or restaurant chain. You have 100 or 1,000 different locations, and you are allocating your managers and employees to those different locations. Now, you're going to have some additional constraints, but at least one of the constraints is not only that the number of allocated employees or allocated managers should be greater than 0, greater than or equal to 0, but also that the decision variables should be integers, because you cannot allocate, let's say, 7.35 employees to a certain location. It needs to be either 7 or 8 employees. So the decision variable should always be an integer. So now, after writing like what are the decision variables, the objective function, and constraints, I'm gonna now fill out that second table before I use solver. So first of all, for the decision variables, I'm gonna leave those cells empty, and I'm gonna write down the information that I have for the constraints and for the decision for the objective function. In those cells, I'm gonna only use formulas. So here, for example, for raw material A, I'm gonna write down how many units of A I'm gonna use on a weekly basis. So mainly, I'm writing that left-hand side of the equation. So I need to write 2 times x1 plus 3 times x2. So here I put 2, so I'm choosing this cell, times the decision variable cell for x1 plus 3 times the cell containing x2. I'm going to do the same thing for B. So for B, the left-hand side is 5x1 plus 2x2. So this is equal to 5 times x1 plus 2 times x2. Finally, for C, I have 1 times x1 plus 4 times x2. Now for the objective function, my profit, I'm going to write down the function of profit. It's 12x1 plus 8x2. So this is equal to 12 times x1 plus 8 times x2. So now that I did that setup, I have now the table and I'm ready to use Solver. However, Solver may not be available right away. So here, when you click on data, if you don't see Solver available, you need to add Solver. So here I included the steps that you need to follow in order to add Solver. So here, if you click on File, and then here you have add-ins, you click on it, you see Analysis Toolpack, you click on Go, and here you can see Analysis Toolpack, the first one, and the last one is Solver add-in. Now, I need you to add those two, Solver add-in and Analysis Toolpack. Today, we're going to be using Solver. However, we're going to need the Analysis Toolpack in order to perform regression analysis for the second part of the project. So here, I'm going to click on OK. So now, as you can see, I have data analysis and solver available. So now I'm going to click on solver. So I'm going to reset everything. So first of all, you need to determine the cell that contains your objective function. So the cell containing my objective function is G14, this cell. Now, by default, it's set objective to maximize. However, for the project, you're going to be minimizing risk. So you need to choose minimize for your project. However, here I'm going to leave it as maximize because actually here I'm maximizing my profit. By changing variable cells, here I need to choose cells X1 and X2. So I choose those two empty cells, B14 and C14. Subject to the constraints. So now I need to start adding the constraints. Now, the first constraint is that this cell, D14, and this is here by default, it's set to less than or equal, so I leave it as it is. This should be less than 1000, the value that I have here. I click on add. The second constraint, cell E14, the number of units needed from raw material B, they should be less than or equal the available quantity, which is 800. I click on add, and then I add the last raw material constraint for C. F14 should be less than or equal 750. So I click on add. Now, the non-negativity constraints, mainly this cell here, B14, should be greater than or equal, and here I put 0. Finally, x2 should also be positive, greater than or equal to 0. Once I'm done, once I put the last constraint, I click on OK. So now, as you can see, I have all of those constraints. I have my objective function to maximize the cell containing the objective function, and by changing the decision variables cells. So now I click on solve. I click on OK. So here, as you can see now, Solver has generated a solution into those cells B14 and C14. So mainly, to maximize my weekly profit, I should produce 94.44 units of product X1. So mainly here, I can have like decimals with the production, because mainly like I will produce 94 units, and 44% of the 95th unit is completed. The same for X2. I need to produce 163 and 89% of the following unit. If I do this, I would be able to generate a maximum profit of $2,444.44 a week. Now, if you look at the constraints, those are the actual quantities that I have used. And as you can see, I still have some slack regarding raw material A, because for raw material A, I didn't need all the available quantities of A. So I still have like 319.45 or 44 available of raw material A. While for B and C, I used the full quantity. I've used the 800 units of B and the 750 units of C. Now moving to the second example. This is here an example that, that relates to investments. So here I have the following. I have a decision to make, an allocation decision to make, to allocate my wealth or my portfolio into two types of investments. Here I call them equity and debt. So it's like I have E represents an ETF invested or a mutual fund invested in equities. D represents an ETF invested in debt instruments. Now I have here the expected return for equity. It's 10% a year. For debt, it's 5.5% a year. Furthermore, I have here the standard deviation. It's 18% for equity, 11% for debt, and finally I have the correlation between debt and equity at 0.35. So this time, my decision variables are mainly WE and WD. How much should I invest in equity? How much should I invest in debt? The objective function is the standard deviation of the portfolio. My objective is to minimize sigma of the portfolio, the standard deviation. Now, regarding my constraints are going to be related to the target return and to the sum of weights. And let's say that short selling is not allowed. I need also to have non-negativity constraints. So for example, the minimum allocation I can have for debt is 0%. Now, in reality, I can have, let's say, negative 10% or negative 20%. In case short selling is allowed, it means that I'm using the proceeds from shorting debt to invest more in equity, or vice versa. So here I'm gonna Okay, so those cells, they should remain empty. For the standard deviation of the portfolio, I need to write down the formula in this cell. So I'm gonna type in that this is equal, and remember, this is here the standard deviation, not the variance. So it's gonna be the formula of the variance raised to the power 1 over 2, which means the square root of the variance. So here, this is equal to WE squared, this cell, times sigma E squared plus WD squared times sigma D squared, so C13 raised to the power 2, plus 2 times WE, so cell E11, times WD, cell F11, times the covariance. Now here I don't have the covariance, I have the correlation. So I need to multiply by the correlation times sigma E times sigma D. I close the brackets and I raise everything here to the power 1 over 2 or 0.5. So this is how I'm getting the square root. So initially, I'm going to start with a standard deviation of 0 because mainly I'm investing 0% in equity at that so far. I didn't have like any allocation yet. Then I'm going to write the expected return formula. So the expected return of my portfolio is equal to WE, so cell E11, times the return of equity plus WD, the weight of debt, times the return of debt. Now, the target return here, because you're gonna do this in your project, you need to solve multiple times for different target returns. So here I'm including this as a cell instead of putting this directly in solver because it's easier to change it here instead of changing it in solver. So here for the target return, let's say I can start with any value that's between 5.5% and 10%. Because 5.5% is going to be my lower return, 10% is going to be my higher return. Now, in reality, I can get to lower returns or higher returns if short selling was allowed. So if short selling was allowed, if I'm able to allocate, let's say, negative 25% to debt and 125% to equity, I'm going to have a return of the portfolio that's higher than 10%. On the flip side, if I have a negative allocation to equity, meaning I'm shorting equity and I'm investing more than 100% in debt, my return is going to be less than 5.5%. So here, because short selling is not allowed, I need to choose a value that's between 10% and 5%. So let's say I choose 8%. Finally, for the sum of weights, because here one of the constraints for such type of problems is that because I'm allocating everything to either E or T, the weights, the sum of weights should always be equal to 1. So I'm going to put simply that this is equal to WE plus WD. I don't here need to add, let's say, an additional cell like the target weight because I know that this is always going to be 1. So I need to write it only once as a constraint in solver. So now after you finish the setup, you can go to solver. Here I need to reset all. So I click on this one to remove the previous entries. Okay. So now my objective this time is the cell containing the standard deviation. So I click on it. So it's cell G11. However, here you need to be careful because here I have the objective set to maximize. So I need to change this to minimize because I need to minimize risk, not to maximize risk, by changing the weights allocated to E and D. So those are my decision variables. So I choose those cells, E11 and F11, and now I start adding the constraints. Now, the first constraint is the return constraint, meaning the return of the portfolio should be equal. So I change this to 8%. So here I'm choosing the cell I11 that includes the target return of 8%. I click on add. Now I'm gonna add the weights constraint. So I'm gonna say that this cell J11 should be equal to 1. So unlike the target return you're gonna see later on, I need to change it whenever I solve. However, for this constraint, the weights constraint, it's always gonna stay the same. So that's why I didn't have a separate cell for the target weight. So I click on add. Finally, I need to add the non-negativity constraints. For the non-negativity constraints, I need to say that WE should be greater than or equal to 0. I click on add. WD should be greater than or equal to 0. So as this is my last constraint, I need to click on OK. If you click on add, you're gonna be asked to enter an additional constraint. So now I have everything ready. I click on solve. So mainly this is the solution that I'm getting. If I want a target return of 8%, I should allocate 55.6% to equity and 44.4% to debt. In this case, I would have a minimum standard deviation of 12.57%. Now, once I solve for 8%, I'm gonna copy and paste those cells in the second table. And here, make sure that when you are pasting, so let me copy first. So when you are pasting those cells, you need to choose values. So here I changed my selection to values. Now, let's say that I need to solve for a target return of 10%, for example. I go now right away to solver and click on solve. So this is the solution. If I want 10%, I need to invest everything in equity. So once again, I copy and paste, and here it should be values. I'm gonna do this for 9.5%. So with 9.5%, I would solve again. So here I need to go back to data, solver, solve. So here I have another solution. I copy it and paste it. Values only. Then let's say I'm solving for 9%. So I go back to solver, solve again. Now let's say I want 8.5%. I'm gonna solve. So I copy and paste values only. Now here, if I'm working on deriving the full efficient frontier, I should go all the way back to 5.5%. Here, I'm gonna stop at 8%, so I'm going from 10% to 8%. Here, like on this graph, this is what you see. So this is part of the efficient frontier. But like, let me show you something here. I'm gonna do this for 5.5 and 6%. So let me do 5.5%. So of course here the solution is to allocate everything to that. So I would copy that solution and paste it in that second table. Then I'm gonna here choose a target return of 6%. Go to solver, click on solve. So again, I copy and paste values only. So now here, like the efficient frontier is not yet complete. However, you can see this, like this point here is for the portfolio with a return of 5.5% and where the risk of the portfolio or the standard deviation is 11%. Now, as I'm allocating to the riskier asset, which is equities, what happens is that my return is now higher because here I have return as a function of risk. So as I'm allocating more to equity, this point here, what happens is that my return went up from 5.5% to 6%. However, risk went down. So if you can see here, the risk now at 6% return is only 10.64%. So mainly this shows you like the benefit of diversification where the correlation is less than +1. Because here I have a low correlation, there are benefits from diversification. So as I'm allocating to that riskier asset, if you want equities, I'm able to reduce the overall risk of my portfolio below the level risk of debt, which is 11%. So although equities are riskier than debt, when I'm combining the two, I'm able to even get to a standard deviation that's less than the standard deviation of that, the least risky asset. So that's it regarding the application of solver in Excel and how to derive the efficient frontier.